Okay, guys, let's just carry on where we were last lecture. So we were doing this example. And here the example is the vector space 2 of all polynomials of degree less than or equal to 2. So just for instance, those would contain all the constant polynomials, it would contain all linear polynomials, and all quadratic polynomials, etc. Okay, so this is the vector space we're looking at. You can check that this is a vector space by verifying the 10 vector space axioms. And here the question is, does the set x plus x squared, x minus x squared, 1 plus x, 1 minus x, span P2? Okay, and here's the solution. The answer is yes, and you can see it as follows. So take a general element in P2. So a general element has a form ax squared plus bx plus c, and this is going to be a general element in P2. Okay. Then we know that this element ax squared plus bx plus c is in the span of this setup here, if and only if, so this is just definition, so if and only if there exists lambda 1, lambda 2, lambda 3, and lambda 4 such that lambda 1 times x plus x squared plus lambda 2 times x minus x squared plus lambda 3 outside of 1 plus x plus lambda 4 outside of 1 minus x is equal to our element ax squared plus bx plus c. Okay, and so let's just collect like terms in this polynomial, right? So collect all the x squared terms. We get x squared outside of lambda 1 minus lambda 2, and that's all. And then collect our x terms. Our x terms, we get lambda 1 plus lambda 2 plus lambda 3 minus lambda 4, right? And then finally we have our constant terms. So our constant terms are going to be lambda 3 and lambda 4. Okay, good. And of course, we're setting this equal to ax squared plus bx plus c. Okay, so this looks confusing because actually we have 4 unknowns on the left-hand side and 3 unknowns on the right-hand side, and that kind of just seems like too much to deal with. But actually, this turns out to be quite manageable. Okay, so we just want to set like coefficients. So on the left-hand side, the coefficient of x squared is lambda 1 minus lambda 2, and on the right-hand side, it's a. And similarly for the coefficient of x, and also for our constant terms. Okay, so this becomes a system of 3 equations in a multitude of unknowns. But let's just write down the system. Okay, so here the system, our first equation, referring to the x squared terms, is going to be lambda 1 minus lambda 2 equals a. Okay, fair enough. Now our second equation is going to be lambda 1 plus lambda 2 plus lambda 3 minus lambda 4 is equal to b. And finally our last equation is lambda 3 plus lambda 4 is equal to c. Okay, so we have a system of equations, and now we just row reduce. Okay, so this actually turns out not to be too bad. Okay, so doing the row reduction, here I'm going to, well, first let's write down the augmented matrix. It would be 1, 1, 0, minus 1, 1, 0, 0, 0, 1 minus 1, 1, 1, and then on the other side we have ABC. Okay, good. And now do our row reduction. So let's see, let's do row 2 minus row 1. Okay, so the first and bottom rows are unaffected. And what happens to the middle row? Okay, so the middle row, we get a 0 here, 2, 1, minus 1, and then here we get b minus a. Okay, fair enough. And just continue the row reduction process, right? So now we're gonna do 1/2 row 2. Okay, so again, top 2 rows are totally unaffected by this, right? The top row and the bottom row, that is. 1, 1. Okay, and so in the middle we get 0, 1, 1/2, minus 1/2, b minus a over 2. Okay, and so now we have it in row echelon form. This is good. And right away from the row echelon form, okay, from this row echelon form, so what do we see? We see every column, or every row has a pivot. Well, let's not overcomplicate things. We see that the system is consistent. Okay, meaning at least one solution, lambda 1 up to lambda 4 exists. Okay, so this is just looking at the pivots. So look at the pivots of who? Look at the pivots of this guy. Okay. Okay, this is good shape. And so we know at least one solution exists. So the conclusion, there exists lambda 1 up to lambda 4 such that, so I don't remember what the vectors were. It was lambda 1 times x plus x squared plus lambda 2 outside of x minus x squared plus lambda 3 outside of 1 plus x plus lambda 4 outside of 1 minus x is equal to our general element ax squared plus bx plus c, which implies that this element ax squared plus bx plus c is in the span of this whole thing we're trying to figure out, right? So all those guys from the start of the question, and then since A, B, C can be anything, right? So this can be any element in P2. We see that P2 is spanned by this set, right? So the set from the start of the question, which I'm too lazy to write the whole thing down again. Okay, so that's that exercise. That's good. And now we're going to move right on to linear dependence. So this is the next section here. Linear dependence. Okay. I'm going to have a nice sip of my coffee. Okay, so carrying right on here. We have the definition. Let's make sure that we're recording. Looks like we are. Okay, so we have the following definition. Vectors v1 up to vr in some vector space v are linearly dependent if the equation lambda 1 v1 plus dot 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 lambda r vr equals 0 admits a unique solution. Okay, and so of course it admits one solution. It admits the trivial solution where all the lambdas equal 0. So in fact, the unique solution would be this solution where all the lambdas are equal to 0. Okay, good. So that's the definition, and let's just go through some equivalent interpretations. So, equivalently, we have, so these are linearly dependent if and only if none of them, so no VI is a linear combination of the remaining VJs. Meaning, so no vector in this list can be expressed as a linear combination of the other vectors in the list. Okay, so that's one equivalent formulation. Let's go for one more here. So I forgot to make this a full sentence. So these guys, what I meant to write up here is are linearly independent. Okay, so equivalently, these guys, V1 through VR, are linearly independent if and only if the removal of any one of them changes their span. Okay. Basically, each of them is like crucially important for the span. If you remove any one of them, you get something different. Okay, so there's a few interpretations of the linear independence condition. Let's just go through some examples. Any set containing 0 will not be linearly independent. Okay, and so any set containing 0 will not be linearly independent, and so you might have guessed this is another way of saying this is linearly dependent. So, e.g., or i.e., will be linearly dependent. Okay, so that's good. Here's another important example. The standard unit vectors I hat, j hat, k hat are linearly dependent or independent. Okay, and we can generalize this to the following example. More generally, the standard unit vectors in Rn, right? So these are, we wrote them as E1 through En elements of Rn, are linearly independent. Okay, and so for both of these examples, let me maybe ask why, right? So we'll see how linear independence and dependence is demonstrated. We'll see this later, and then you can come back and prove to yourself that these three examples really do what I say they do. Okay, and now let's actually do an explicit computation. Okay. And so we're going to ask, or V1 equals to 1 minus 2, 3. V2 is equal to 5, 6 minus 1. And V3 equals to 3, 2, 1. Linearly independent. Okay. So whenever you want to determine if a set is linearly dependent or independent, it just amounts to solving a system of linear equations, which at this point we're pros at. So let's get into it. So of course the equation we're interested in is lambda 1 v1 plus lambda 2 v2 plus lambda 3 v3 equals 0, right? So of course it would be the 0 vector. This is the linear independence equation, and our unknowns, the unknowns of this linear system, are lambda 1, lambda 2, and lambda 3. Okay, and this is, standard procedure to solve. Okay, so, let's expand the v's using this form and do our scalar multiplication of the lambdas and everything, and the system becomes the following. Okay, so the system would become lambda 1 plus 5 lambda 2 plus 3 lambda 3 equals 0. That's our first equation. The second equation is then minus 2 lambda 1 plus 6 lambda 2 plus 2 lambda 3 is equal to 0. And the third equation is then 3 lambda 1 minus lambda 2 and then plus lambda 3 equal to 0. Okay, so this is the system we get. Of course, it has a solution because it's a homogeneous system, but we want to know that that solution is the unique solution. Anyway, you guys know how this go. We go to the augmented matrix, right, which may as well write it out real quick. So the augmented matrix is 1, minus 2, 3, 5, 6, minus 1, 3, 2, 1, 0, 0, 0. Okay, here's our augmented matrix. And then we're going to do our row reduction, right? You guys know how to do this. Okay, and after we row reduce, what do we get? Okay, so we row reduce, and this is what we get. We get 1, 0, 0, 0, 1, 0, 1 half, 1 half, 0, 0, 0, 0. Okay, so I didn't show you the full row reduction, but I'm sure you guys can figure it out. Okay, so we got this, and then what does this tell us? Well, if we look down here, this last row is telling us one free variable, right? Okay, so and one free variable implies infinite solutions, implies no unique linear combination, lambda 1 up to lambda 3. Well, let me just, what am I doing? Lambda 1, lambda 2, lambda 3 implies the vectors v1, v2, and v3 are linearly independent. Okay, so that's how you do that. That is that example. All right. So just to spell out the moral of this example. Moral. Testing for independence. This is just the same thing as solving a system, okay, which we know how to do. All right. Okay, so maybe let me just go through one more quick example. It's basically the same idea, but one more quick example here. So one more quick example, we're going to look at, let's make sure we're still recording. I believe we are. So we're going to look at V1, 1, 2, 2, minus 1, 1, 2, 2, minus 1. V2 is equal to 499 minus 4, 499 minus 4. and then v3 is equal to 5, 8, 9 minus 5. 5, 8, 9 minus 5. Okay. And the question is, are they linearly independent? And here's how we solve it. Okay, so again, just set up your equation. Lambda 1 v1 plus lambda 2 v2 plus lambda 3 v3 equals 0. This is the linear dependence equation. Okay, turn this into a system. So the system would then be lambda 1 plus 4 lambda 2 plus 5 lambda 3 equals 0. 2 lambda 1 plus 9 lambda 2 plus 8 lambda 3 equals 0. 2 lambda 1 plus 9 lambda 2 plus 9 lambda 3 equals 0. And let's top it off with the last one, which is minus lambda 1 minus 4 lambda 2 minus 5 lambda 3 equals to 0. Okay, and so let's just skip through the details here, right? You solve this system, right? You guys know how to solve. And what do you end up with, right? So you end up with the following reduced row echelon form: 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. Okay, and we're not done. We also have a row of zeros at the bottom. Okay, and this tells us we have a unique solution, right? So if these are lambda 1, lambda 2, lambda 3, then this tells us that lambda 1 equals 0, lambda 2 equals 0, lambda 3 equals 0, implies our unique solution, implies, yes, these vectors are independent. Okay, so that's how you do that. Oh, okay, so of course I made a mistake back here. Influence solutions, no unique. So of course, because it's not unique, this means that they are not linearly independent. And then in this case, we found there is a unique solution, and so that they are linearly independent. So a little mistake there. Okay, let's carry on. Right, so I'm not going to do this example right now, but I'll just say this is like a good exam question. So example, which I won't do. It's a good exam question. Okay, here's the example. We're going to take u is equal to 1 minus x. V is equal to 5 plus 3x minus 2x squared, and W is equal to 1 plus 3x minus x squared. Okay, and the question is, are these independent? Are these linearly independent? And of course, linearly independent in the ambient vector space P2 of polynomials of degree at most 2. Okay, so this is a good question for you to try. You can look at the textbook. You see a whole bunch of these kinds of problems. All right, carrying right on with the lecture so that we can eventually get to the weekend. Okay, let's look at some special cases of linear independence. Guys, don't mind me. I'll be back in a sec. I just gotta point a fan at myself. Okay. All right, I'm back. Coffee time. All right, let's go. So, first, a set of a single vector, right? So if we only have a single vector in our set, and that vector is V, this set is independent if and only if if and only if v is not the zero vector. Okay, so graphically here, zero vector, this set is not independent. Okay, but if our set is just some non-zero vector, here's our v. Right, so on the right, if that's our v, it's a non-zero vector, then this set is independent. Okay, so that's when you only have a single vector to worry about, really not that hard. Okay, now let's look at the case of two vectors. A set of two vectors is independent if and only if v1, so the two vectors here, two vectors are going to be v1, v2. If and only if v1 and v2 do not lie on any common line through the origin. Okay, so lying on a common line, that's the same thing as saying, i.e., v1 is not equal to t times v2 for any scalar t. Okay, and so just let's visualize the different cases which can occur here. Okay, so of course we have the case where v1 is 0, and that's also the same as v2. Okay, then our set is just a single point, right? And this is not independent. Good. So there's one case. Okay, here's another case. Okay, so this is going to be maybe v1 and v2 are both non-zero. v1 and v2 are both non-zero, but they lie on this common line. They both lie on this line. Okay, so now since they both lie on this line, this is again a not independent case. Right? Now maybe one vector v1 equals 0, but the other vector v2 is non-zero. Okay, again, this puts us in the independent or not independent category. Okay, so none of these examples are independent. The example where they are independent would be if here's our v1 pointing off in one direction, here's our v2 pointing off in another direction. They do not lie on a common line, right? So the lines they determine are not identical. And so in this situation, this is when you do have independence. This is the independent case. So just trying to visualize the situation a little bit here. Okay, and so let's just take a quick look at the set of the case when we have three vectors. Okay, so a set of three vectors, v1, v2, v3, is independent precisely when no plane through the origin contains all three. Okay, so you can kind of see a pattern here. If we go back to when we only have a single vector, this single vector is independent if and only if no point through the origin, right, let me grab my laser pointer. If and only if no point through the origin contains that v. Now in the second one, when we have two vectors, we see they're independent if and only if no line through the origin contains both vectors. And you just boost it up one dimension, and then we see that three guys are independent if and only if no two-dimensional plane contains all three. Okay, so this should give you sort of a geometric picture of what's happening in general, okay? And so just a little picture here, right? So maybe you have, right, so V1 could be like 0, 2, 2, or let's do 2, 2, 0, for example. V2 is equal to 1, 2, 0, and here's our V3, and our V3 is equal to 0, 1, 0. Okay, good. Now what we notice, you know, the ambient space here is R3, okay? And all three vectors have this z component of 0. So all three lie in the xy plane, okay? Right, so maybe, you know, this isn't the best drawing, but maybe that's kind of me drawing our xy plane. And so this implies that they're not independent. Okay, good. And now, for example, where they are independent, maybe this is our V1. Here's our V2. Here's our V3, right? And we can look at the plane containing V1 and V3, that's this plane. And we can look at the plane containing V1 and V2, that's this plane. And we can look at the plane containing V2 and V3, that's this plane. But no plane contains all three, right? And so this would be the case where they are independent. Strong independent vectors. Okay, good. All right, okay, so let's top this off with a little theorem here. A set of independent vectors in Rn has at most n vectors. Okay. So this is a really important theorem. Let's try to discuss the intuition a bit. So the way to interpret this is as saying you can't fit 3 dimensions into 2. Okay, or, you know, or whatever it is, or, you know, 6 into 4, or 7 into 6, right? So you can't take something with a higher dimension and fit it into something with a lower dimension, right? So in this case where we had the 3 independent vectors, no plane contains 2 of them, right? So try to imagine we have 3 vectors in R2. Here's R2, and now we have 3 vectors. Well, R2 is itself a plane, right? So automatically, we see that these 3 vectors are contained in some common plane, right? And so this implies they're not independent. And when you're interpreting this theorem I've just written here, this is the picture to have in mind. If you try to have a set of 3 independent vectors in a 2-dimensional space, such as R2, this is equivalent to trying to fit 3 dimensions into 2, and that's just not possible. How could you crush all of 3-dimensional space into this flat sheet of paper? It just, on the level of intuition, it just doesn't work. Okay, all right, so now the last topic for today, which I'm not going to get very far into, I just want to touch on this topic in preparation for next lecture. And I know I'm being a bit fast and loose. We had technical difficulties. I want to have a weekend. We're all tired. So, you know, email me if you have questions. Come to my office hours. This is a fast and loose lecture. And let's top it off with this one final quick topic. Okay, so this is 4.5 coordinates and bases. Very cool topic. A physicist would tell you it's the whole point of this class, and I would tell you not to talk to physicists. Okay, 4.5 coordinates and bases. So here's just a little thought experiment. And I just want to introduce this thought experiment. and then end the lecture. We won't do any fancy math after this. So a thought experiment. And so in this thought experiment, we have a vector. I've picked the vector 1, 2. And this vector resides in the two-dimensional plane, in R2, right? Here's our R2, our 2D plane. Okay, and so let me draw our x-axis and our y-axis. Okay, and we always come back to our x. Don't ask why. Okay, so what's going on here? Our vector is 1, 2, so it has x-coordinate 1 and y-coordinate 2. So this is going to be our guy right here, 1, 2. Okay, fair enough. And the reason we give it the coordinates 1, 2 is because if you look at the x-coordinate, it hits the x-axis at x equals 1, and it hits the y-axis at y equals 2. Okay, we all know this. This is high school stuff. But what if we use different coordinate axes, right? So instead of this y-axis and this x-axis, what if we used different coordinate axes? What if we changed the axes? Okay. And so let me try to make a bit of a schematic picture here. So I'm going to copy paste the same thing. Okay. So here's the picture I just drew. And I'm going to just fade this whole picture away. Aside from maybe that. Okay. So let me just make this faded. And how do I want to do that? Sorry, technical difficulties, guys. Okay, let's go black. Let's go to the color wheel, and then let's fade it so that it's like here. Okay, that's fine. Okay, so I have the faded axes here. But now what if we use a different choice of axes? So instead of this x-axis and this y-axis, here I have some other axis. Maybe this is our x prime axis. Who cares, right? So let's give this a different variable name. And here we have a whole other axis. And these axes are crazy, right? So this could be our y prime axis. These axes don't even meet at right angles, right? They're very strange axes. Why would anyone work with these? Well, I don't know why, but the point is you could. And here's our point, right? So this is still the vector v we care about. Here's our vector v. And we can see the old coordinates were 1, 2. But if we wanted to describe it with this new coordinate system, well, we'd have to do something different. So with this new coordinate system, well, let's go to the x prime axis, but traveling parallel to the y prime axis. And we trace out this line here. Okay, boom. And we hit the x prime axis here. And just for example, I don't actually know, but just for example, let's say it's hitting the x prime axis at x prime is equal to 4. Okay, so this is not to scale. This is just a thought experiment. Okay, and so now let's find the y prime coordinate. So to find the y prime coordinate, you'll travel to the y prime axis, traveling parallel to the x prime axis. Okay, so that's going to look like this. Boom. Okay, here we hit the y prime axis, and maybe this is y prime equals 1. Okay, and so before we looked at v, and we had our x and y axes, and we got the coordinates 1, 2. Okay, well, what happened now? Now we look at v, and we have this new set of coordinates where the x coordinate is now 4, and the y coordinate is now 1. Okay, and just abstractly speaking, which one is correct, right? Maybe you naturally say, so here's the question. Does v equal 1, 2, as it did with our xy axes, or does v equal 4, 1, as it did with our x prime, y prime axes? And the answer is, it depends on your choice of axes. Right, so we're so used to working with the XY axes. We have this thing called XY brain, but there's nothing special about the XY axes. And in fact, it's extremely important in math and physics to be able to work with different coordinate systems than just the standard XY or XYZ or, XYZT for time axes. You need to be able to change axes, and this becomes very, very important. And so now what we want to do, so the goal of this section of the course, basically the last topic in this course, which we'll cover next lecture, the goal is a means of translating between the two coordinate systems. Okay, all right. So that's all for now. I'll see you guys on Monday. You have your final exam on Wednesday. Expect more details on that coming up. I have nothing else to say. Goodbye.